everybody, Mr. Brown here. In this video we're going to talk about dimensional analysis and how to use it to solve problems in physical sciences such as chemistry and physics. So in dimensional analysis we use conversion factors to go from one unit to another. And conversion factors are relationships that relate one unit to another. And there's a few examples here on this slide of some different conversion factors that you may already be familiar with. And they are things that say, for instance, there are 24 hours equal to 1 day. There are 12 inches in 1 foot. And there are 1,000 milligrams in 1 gram. When we do or carry out dimensional analysis in chemistry, we will often be using these and expressing these as ratios, as mathematical ratios, and you can often see them written in this type of format. So if I want to show that 24 hours equals 1 day in mathematical form, I can write it either as 24 hours per 1 day or 1 day per 24 hours. And I can show all of the units in that same method. 12 inches in 1 foot, or 1 foot is 12 inches. And then finally for the last one there, I can say that 1,000 milligrams per 1 gram, or 1 gram per 1,000 milligrams. And we'll be able to use these expressions to convert units that we are given to units that we want to know. Sometimes you may need to determine your own conversion factor based on the relationships between different SI units and what prefix is in front of them. And to do so, you may want to look at a chart somewhat like you see here, where we have the base units in the middle and each of the prefixes laid out in steps beyond them. We have the lowercase d for the deci, and the lowercase c for the centi, and the lowercase m for the milli. And we have capital D for deca, capital H for hecto, and capital K for kilo. And so if I wanted to know, for instance, how many milligrams were in 1 gram, then I would count. That is 1, 2, 3 steps away. And you can see there that every step represents a multiplication by 10. And so if you're moving from the smaller units to the bigger units, that means there would be 10 times 10 times 10, meaning there are 1,000 millimeters in, or 1,000 milligrams in 1 gram. I'm talking grams, sorry. And so you basically, all you have to do is figure out how many steps away there are and multiply that many times by 10. And you have to keep straight in your head which is the bigger unit, which is the smaller unit, which you would have more of and which you would have one of, to do those relationships. You can see there on the bottom I provided probably all of the ones that you'll use most often here in chemistry, at least. And so if you can keep those straight in your head, you'll do well going forward. All right, on this slide we have a set of rules to kind of tie this all together and have a sequential set of steps for following when we're doing dimensional analysis and problems that are solvable with dimensional analysis. The first thing we want to do is identify the units we're starting with, or what the problem gives you. What information do you have, and how are you being asked to manipulate that information? That goes along with number 2. Identify the units of your answer. Identify what you're being asked and how would an answer for that question sound. What units would be would be appropriate to answer that question at the end. And then after that, you can start to determine what conversion factors are necessary to accomplish that transformation. What information do I need? What kind of relationships can you give me that will allow me to complete this movement from one unit to the other? And then finally, we're going to put the given value first, put that very first piece of information, and arrange the conversion factors as multiplications of fractions so that the units cancel and give us that final unitary answer that we want. The best way to look at these perhaps is always by example, and so on the next quite a few slides we have some examples put together of how to implement these steps and use dimensional analysis to solve many types of problems in physical sciences. All right, on this slide we're going to look at how to convert 261 grams into kilograms using dimensional analysis. And we know that step one of our process is to write down the given value. And I like to put the given value, because we're going to be multiplying a lot of ratios which look like divisions, I'm going to put the given value over 1 if it's only just a single unit. For instance, in this case, I will write 261 grams, and I'm going to put it over the number 1. I haven't changed anything by doing that. Dividing something by 1 just leaves itself, so that's still 261 grams. Now I need to multiply that by a conversion factor that will relate grams to kilograms. We saw on our SI units slide that there are 1,000 grams in 1 kilogram. And we also talked earlier about how we can use that to set up one of these conversion factors, how we can write that. We can either write that as 1,000 grams per 1 kilogram, or 1 kilogram is 1,000 grams. And we want to pick the conversion factor that will allow us to cancel the unit we no longer want and arrive at the unit we do want. So we see 261 grams over 1 with grams in the numerator. If we can multiply that with something that has grams in the denominator, we can cancel that grams unit and see what units we're left over with. So we're going to pick this unit conversion factor right there and do 261 grams times 1 kilogram is 1,000 grams. We can see there, now we have a grams in the numerator and a grams in the denominator, and so when that operation would be carried out, the grams would divide into 1 and essentially cancel each other. We're still left with a unit. We're left with a kilogram unit, which is what we want our answer to arrive at. So we can see now the dimensional analysis has told us the math we need to do. We need to multiply 261 times 1 and divide that by 1 times 1,000. That's essentially 261 divided by 1,000. And then we keep our unit that we have left over, our kilograms. And so if we do 261 divided by 1,000, that will tell us that 261 grams is equal to approximately 0.261 kilograms. Here on this slide, we are asked to convert 3 days into seconds. This is a good problem for a couple of reasons. First of all, it's going to be one that you probably would be expected to kind of come up with your own conversion factors, because you know already the conversion factors that will help you solve this problem, even though you may not know them as conversion factors right now. So we're going to try to convert 3 days into seconds. I personally don't know the day to seconds conversion relationship, but I do know a multitude or a few different relationships that will help me go from the day unit down to the second unit. And I will start by listing those out. So I know that, make sure my pen's up, I know that 1 day is equal to 24 hours. I feel pretty confident about that fact. And I know that 1 hour is equal to 60 minutes. Pretty comfortable as well. And then I know that 1 minute is equal to 60 seconds. So using these 3 different conversion factors, I think I can take my 3 days unit and move down to 3 seconds, or however many seconds there is. We like to start by writing what we're given. I like to put it over 1 so that I can keep all my multiplication straight. And I want to go to seconds, but I can't do that right away, or I can't do that in one step. So I'll start by trying to cancel out the days, because I know at the end of my problem I don't want any more information about days. So I will use the only conversion here I have that says 1 day is 24 hours, and I can either use that as 1 day over 24 hours, or 24 hours per day. And since I'm trying to cancel days in the numerator here, I will try to put days in the denominator here, and that is going to be this conversion factor, 24 hours per day. Now I know when I do the math on this, because I have days in the numerator and days in the denominator, that they will cancel each other out. And if I stopped there, I would be left with however many hours 3 days is. And that's pretty intuitive, because we see it's 3 times 24. However, I don't want to stop at days. I want to go all the way down to how many seconds that is. Or I don't want to stop at hours. I want to go all the way down to however many seconds that is. So now I still can't do straight conversion of hours to seconds. Although, if you're pretty good at the multiplication right there, you might be able to know that one. But we're going to take it through minutes first. So I see I have this conversion factor that will help me convert hours into minutes. And again, I can use it. 1 hour is 60 minutes, or 60 minutes is 1 hour. And since I have hours in the numerator here, I want hours in the denominator here to have it canceled. So the conversion factor that looks like that says that there are 60 minutes in 1 hour. That will allow us to cancel the hour units. And then finally, I think we can take minutes to seconds. That's a pretty straightforward relationship on that one. 1 minute is equal to 60 seconds. And as always, we can write that either as 1 minute is 60 seconds, or 60 seconds is 1 minute. Since we have minutes in the numerator here, we are going to want minutes in the denominator here. When we cancel those minutes, now we are finally left with the units that we want our answer to be in. We're finally left with the second unit, and everything else is canceled out. So what we're left with is the math to do. So we kind of look and see what the actual arithmetic is, and it says to do 3 times 24 times 60 times 60. And if we multiply across the bottom, we see that's all 1. So that would be whatever our answer is divided by 1, which would be itself. And when we punch that in the calculator here, we see that that number comes to 259,000 200 seconds. And so there are 259,200 seconds in 3 days. And I really like that problem because it shows that this dimensional analysis stuff makes sense and works using a problem that you would probably be able to solve in this fashion even if you didn't know that you were doing dimensional analysis. And that shows how useful it can be in other areas as well. Here on this slide, we are going to convert 9,474 millimeters to centimeters. This is a little bit more straightforward of a problem, honestly. So we will write down what we know. We know that there are 9,474 millimeters that we are being asked to convert to centimeters. And I need to determine some conversion factors that will help me move from millimeters to centimeters. And we looked at a few of those on our SI unit slides. We may remember that there's a pretty straightforward conversion that says that there are 10 millimeters in 1 centimeter. And of course we can write that one of two ways. We can say that there are 10 millimeters in 1 centimeter, or we can say that there are 1 centimeter for every 10 millimeters, and pick the correct style of conversion factor there. We have millimeters in the numerator here. We probably want millimeters in the denominator down here to get it canceled. And if we use the 1 centimeter for every 10 millimeter conversion factor, we will cancel our millimeters and we'll be left in that unit that we want, the centimeter unit. And we'll see that when the math is all said and done, we would need to multiply 9,474 times 1 over 1 times 10. So that becomes 9,474 divided by 10, which would be 947.4, and then we're left with the centimeter unit, so we can say that is 974.4 centimeters. So 9,474 millimeters is 947.4 centimeters. Here on this slide we have our first example of where we are converting some mixed units, and in fact we are going to convert the entire unit, both the units sitting in the numerator and the denominator in this problem. We're going to investigate some of the information we're going to need to know to do this. We'll first start by writing down what we already know. We know that we have some substance that has a density of 8.41 grams for every 1 milliliter of volume of that substance, and we want to convert that to a different unit of density. We want to know what 8.41 grams per milliliter will convert to in kilograms per liter instead. And we need to know some conversion factors that will help us go from both grams to kilograms as well as milliliters to liters in order for this to work. So let's write down the conversion factors that will help us to make this happen. We're going to need to know that for 1 kilogram there are 1,000 grams. We're also going to know that for 1 milliliter, for 1 liter there are 1,000 milliliters. And we can already investigate how we can write those conversion factors either with the, for instance, kilograms in the numerator or the grams in the numerator, either or, and use them in our conversion here. So to approach this, I need to pick one. I need to either change the grams or the milliliters, so I'll start with the grams. I know I want to take the grams and convert it to kilograms. So I need to use a conversion factor that will leave me with kilograms in the numerator, because kilogram is in the numerator here, and cancel out the grams. If I can use the conversion factor that says there is 1 kilogram for every 1,000 grams, that will allow me to cancel my grams and be left with kilograms in the numerator, which is ultimately what my problem is asking for, so that's good. The next thing I do is try to get rid of the milliliters and be left with liters in the denominator here. So I will say that for every 1,000 milliliters, you have 1 liter of volume. Since milliliters is in the denominator here and the numerator here, they will cancel. And we will be left with liters in our denominator. Our answer needs to be in the units kilograms per liter. And after all of our units are accounted for, that's what's left. All that's left after that is to do the math. 8.41 times 1,000 would be 8,410 divided by 1 times 1,000 times 1,000 is 1,000, which will ultimately calculate back out to 8.41 kilograms per liter. So grams per milliliter and kilograms per liter, since both of the units grow, they're actually equivalent units. 8.4 grams per milliliter is the same density as 8.41 kilograms per liter. Alright, on this slide we are going to attempt to convert 3.8 kilometers per second, a measurement of velocity, to miles per year, which is another measurement of velocity. This is one of the questions that if you ran into on a test, you'd probably be given at least one of these conversion factors, and that would be the fact that there are about, there goes my slides moving again. Alright, there are about 1.6 kilometers in 1 mile. And then certainly you would have to determine the set of conversion factors that you would need to use to go from seconds to years, and those might look something like this. There are 60 seconds in 1 minute. There is 1 minute in, 60 minutes in 1 hour. There are 24 hours in 1 day. And there are 365, we'll just stick with the regular 365. 365 days in 1 year. We'll kind of ignore the leap year thing for this problem. So we can see that the distance conversion there, kilometers to miles, is going to be rather simple, where we're going to have to set up multiple steps to go from seconds to years. But that's okay. Let's start with the distance, since we know it already. Write down what we know. 3.8 kilometers per second is our velocity that we're traveling at. We want to know how many miles we can go in a year at that velocity. So we're going to convert those kilometers to miles times, we have kilometers in the numerator here, so we want it in the denominator here to get it canceled out. We would prefer if miles ended up on top, and that's the way it would seem if we use the fact that there is 1 mile for every 1.6 kilometers. We have our kilometers canceled and we have our miles in the numerator, so that's taken care of. Let's go about converting that seconds into years instead. We want to cancel seconds in the denominator, so we're going to put seconds in the numerator here. There are 60 seconds in 1 minute. It gets rid of seconds for us, but leaves us in minutes, and we want that bottom numerator unit to be in years. So let's keep going with this. Let's cancel the minutes there. There are 60 minutes in 1 hour. And as well, that cancels minutes but leaves us in hours, so we're not done. Let's go with the fact that there are 24 hours in 1 day. And finally, to get rid of that days, we're going to go with the fact that there are 365 days in 1 year. So if we cancel the days there, finally, we see that we would be left with year in our numerator, and we still have the miles up here back at the beginning in our denominator, and we want our answer to come to miles per year. So looks like we've set up everything we need to set up. All that's left is to do the arithmetic. We can see that the top has a good bit of multiplication. That would be 3.8 times 1 times 60 times 60 times 24 times 365, and that gives us a very large number, 119,836,800. And then on the denominator side of things, it looks like a bunch of ones except for the 1.6. So that big figure would then be divided by 1.6. And the total answer would be 74,898,000. miles per year is our velocity. So that's really pretty quick, and that is pretty quick. Kilometers are big distances, so if you're traveling 3.8 of them every second, that would relate to a very, very large amount of miles traveled over the entire year. So we can be pretty confident that our answer makes sense here. Here on this slide, we have a different example of how to use dimensional analysis. This time we can see we're not really being asked to convert something, we're being asked to solve a problem. This sounds more like a physics problem, a velocity style problem, but we're going to use it to set an example of how we might solve problems using dimensional analysis. So we can see it says, or we're being told, we have a velocity of 65 miles per hour, regular highway speed, and wherever we're at apparently is 125 miles to San Diego, and we want to know how many minutes it's going to take us to get to San Diego from that distance with that velocity. And one of the things we might want to understand about problems like this is when we're given these mixed unit problems like we see here, where it says it says we have a velocity of 65, there goes the slide. It says we have a velocity of 65 miles per hour. If we write it out like that, we might see that this looks like one of those conversion factors that we've used in other problems, and it is, and it can be treated just like one of those conversion factors. We can write it as 65 miles per hour, or we can write it as 1 hour will carry us 65 miles. And so we can use that in our dimensional analysis here to cancel out units where we need to. And because if we start with what we know we have 125 miles to travel. And we also know that we can go 65 miles in 1 hour, or 1 hour takes us 65 miles. We can then use that, we can put our 125 over 1, and then use that 1 hour as a conversion factor to cancel our miles. And we would be left with hours at that point. So this math here would tell us how many hours it would take to go to San Diego from 125 miles away at 65 miles per hour. Of course, we can, if we're reading closely, we see that the problem ultimately wants us to answer in minutes. So now we need a conversion that will take us from hours to minutes. I think we know that one pretty well at this point. We know that there are 60 minutes in 1 hour. And so if we do our cancellations there, we're now left with the unit solely that we want for the answer, minutes. So, and then the math says to do 125 times 60. And then on the bottom there, we see we're going to divide by 65. And that comes up to about 115.4 minutes. So at 65 miles an hour from 125 miles away from your destination, it's going to take you right at 2 hours to get there, which is certainly a reasonable answer if you look at the question involved. Here on this slide, we have an example a little bit more tuned to chemistry. It reads, as an instructor is preparing for an experiment, he requires 225 grams of phosphoric acid. The only container readily available is a 150 milliliter Erlenmeyer flask. Is it large enough to contain the acid, which has a density of 1.83 grams per milliliter? So we saw on the last side how when we're given those mixed units like that in a problem, we can go ahead and treat that as one of our conversion factors. So we could say that phosphoric acid has a density of 1.83 grams per milliliter, or we can say that there is 1 milliliter for every 1.83 grams of phosphoric acid. So using that information, we can start with the fact that we have 225 grams necessary for our experiment. We're going to multiply that by the fact that we want to get rid of the grams because we want to know how much volume this 225 grams is going to amount to. So I'm going to multiply that by 1 milliliter for every 1.83 grams. And that will allow me to cancel grams and be left with milliliters. Then I can check to see if my container is large enough. So I'll do 225 divided by 1.83, and that means that 225 grams of phosphoric acid has a volume of about 122.9 milliliters. And so we can say that, yeah, our container would be just big enough to hold the 122.9 milliliters of phosphoric acid.